All right, friends, welcome back. This is going to be part one of a two-part video series I'm going to do here on section 4.1 of your textbook. We are going to be starting chapter 4 in this video, and in this video specifically, we're going to be taking a look at reciprocal functions and basically just take a look at a bunch of characteristics of their graphs so that we can go ahead and sketch them by hand whenever we need to. So, first of all, getting into what a reciprocal function is, the most basic type of a reciprocal function is just f of x is equal to 1 over x, and this is your simple function machine that just simply finds the reciprocal of whatever you give it. Okay, the graph of that function is over here, and again, just so we can kind of get a better feel for what this function does, if you give this function an input of positive 1, then the reciprocal of that number is positive 1 itself, which is why we would go up to 1 and then plot that point. That would be the first point on this graph. If we give this function machine a 2, then the reciprocal of 2, since you can write 2 as 2 over 1, reciprocal of that, you'll find that that is 1 over 2, or 1/2. So that's why we go up and plot that point, and et cetera, right? If I were to give this a input of 3, the reciprocal of 3 is 1/3, so I would go up 1/3, plot that point, and then you could see how the rest of those points would go. But on the left side of the number 1, let's go ahead and entertain this possibility, right? What if you gave this the input of 1/2? Well, 1/2, if you find the reciprocal of that number, that is 2 over 1, or in other words, 2. So if I go over 1/2, I would go up 1 and plot that point. And you can kind of see how the rest of this would shake out, right? So if I were to go ahead and find a number that was super close to 0, like maybe say that number right there is 1 over 1,000. Okay, that is a number that is super close to 0. If I find the reciprocal of that, then that means that I'm going to go over 1 over 1,000, and then I would go up the reciprocal of that, which is, of course, to 1,000. And you can see here what that would mean for the end behavior of my graph. I'm just going to continue to go up and up and up and up and up and get closer and closer to the y-axis here. Okay, there's a problem, though. If I have an input of 0, that is something I could go ahead and write as 0 over 1, but if I were to find the reciprocal of that, that would be 1 over 0, which is something that is never allowed in mathematics, okay? And so what that's going to mean is that for our graph here, 0 is not going to be an input that's allowed. My curve up here will get closer and closer and closer to the y-axis, or in other words, the line with the equation x equals 0. But it's never going to touch it, and it's never going to cross it, okay? And so we give that idea a name in mathematics, this idea that there is this boundary line that the end behavior of my curve will always approach but never touch or cross. We call that this idea of there being an asymptote. Okay, so this would be an example of a vertical asymptote because it's a vertical line, all right? And it actually goes the same way horizontally here, okay? So the x-axis represents the horizontal line, y equals 0, and for the same reason, we are not going to be able to find the reciprocal of 0, and so that is going to be another example of a asymptote, although that one would be a horizontal asymptote, okay? So the distinct shape of your reciprocal function is just this, and that is why it's in two parts, is because for your positive number reciprocals, that's this piece that's on top, but for your negative number reciprocals, like the reciprocal of -1 is -1, plot that point, it would be all the same reasoning to plot all the rest of the points there. That's why you have these two disjoint pieces of the function formula when you graph it. This shape is actually something we give a name to in mathematics. It's called a hyperbola, and if you start to notice other different types of reciprocal functions, you might notice that we have all the different function formulas looking like this general form. So we have these values of a and h and k, and these are values that we've seen for other different types of functions before, and they always play the same role for the different various functions that we look at here. And so what I'd like to do is I'd like to go ahead and get a couple of examples where we're just observing the characteristics of graphs here. So in this example here, it says f of x is equal to 2 over x minus 3, and then plus 4 at the very end, okay? Now you notice that we have this hyperbola shape, and you may notice that when we go ahead and take a look at where those vertical and horizontal asymptotes might be, we could do that by studying the end behavior of these two curves here. So if I were to look at the horizontal end behavior here, I might notice that the ends here approach this grid line of the grid pattern in the background. And if I just go ahead and take that over to the other side here, go ahead and erase my little circle, then I might notice that this is the dotted line for a horizontal asymptote that I might be able to take a look at here. And if you study how far you might go up to get there, that would be going up 1, 2, 3, 4 grid squares. And so that would mean that the equation for this horizontal line would be the following, right? So this is a horizontal line, and so therefore it would say y equals a number, and that number is just how far you went up to get to that dotted line. And so that would be 4 grid squares here. So that horizontal asymptote would be the line with the equation y is equal to 4. You might remember from earlier this year or another algebra course that we oftentimes at Blue Springs High School call this a HOI. So that is an acronym that stands for horizontal lines have a 0 slope and pass through the y-axis, or in other words, say y equals. And then we strike the difference between that and what we call a VUX. So VUX. That stands for vertical lines have an undefined slope and pass through the x-axis. And remember that a hyperbola will always have a vertical asymptote here as well. And so if you study the vertical ends of my graph, you might notice that they do approach this line in the background on my grid, right? So this would be our vertical asymptote here in this picture. And the equation for that, of course, would look like x equals, because this is a vertical line, a VUX. And then we would just go ahead and say x equals the number that we placed it on. And so if we go from the origin to the right, 1, 2, 3, we can see that that's where it was placed. So we would say x is equal to 3 is going to be our vertical asymptote. Okay, so when we go ahead and write down equations for your asymptotes here, because they are horizontal and vertical lines, we're going to have to remember how we always write the equations down for horizontal and vertical lines, which is in that way, the HOI and the VUX. Okay, now also remembering here, whenever we want to talk about the domain and range of this function, we can always go ahead and do that according to the graph. One of the things that I talked about in a previous video, in a previous chapter, is that when you want to find the domain of a graph, you can go ahead and picture there being magnets on each notch of the x-axis here. And the idea is that these numbers would belong to the domain if I could take these magnets and drag them up or down to touch the graph, okay? Well, I think in all these cases it's pretty obvious. I can go ahead and drag this one up, and I could drag that one up, and all the way down, etc., etc., dot, dot, dot. I could drag these guys up here and touch the graph all the way through, and then even over here. I can go ahead and drag this up to touch the graph. No problem. All of these would be a part of the domain. But there is one issue, and that issue occurs right here at where we place that vertical asymptote. If I were to drag that up or down, then because that's a vertical asymptote, that's a place where my graph is never going to touch or cross, that is going to be a magnet that misses out on my domain completely. So what that's going to mean for us is that when I write my domain, I'm basically going to say my domain includes all of these input values here until I reach that problem value. And then after that problem value, I can pick up again, and then there's more of my domain, okay? So my domain is basically going to say all the numbers you want besides that problem value, all right? And so when I come down here for my domain, that problem value is where I put that vertical asymptote, and that would be at an input of 3. And so I'm going to say that. I'm going to come up here and say I can go from negative infinity all the way until I reach that problem input of 3. And that could be one part, so I say here negative infinity all the way until I reach 3. And then separately, I can start that new set of numbers by saying the set that starts at 3 and goes all the way to positive infinity. Keep in mind that I use this parenthesis here to signify that I'm not including the value of 3. I just want everything leading up to it, okay? And then remember how we always went ahead and drew these two disjoint sets here. We would go ahead and use that union symbol in the middle. So this would be the complete set of all the numbers that are between negative infinity and positive 3. And we're going to unite that with the complete set of all numbers between 3 and positive infinity, and that would represent our domain, okay? For the range, it would be the exact same thing, except we're going to put all of our magnets on the y-axis and drag them left or right to touch the graph. So basically, you could see that the exact same thing is going to happen, except whenever I get to this value right here on the y-axis and try to drag that to the left or to the right, I'm going to miss my graph completely because that's where I put my vertical asymptote. And so my range is going to basically be the exact same thing, except it's not going to include my horizontal asymptote here. So I'd say that my range includes those values from negative infinity all the way until I reach 4, and then I'll unite that with the set from 4 all the way to positive infinity. Okay, so basically just a little bit of review on how you could take a look at the graph of a rational function and find all of its asymptotes and also its domain and range. To save time in the video, I've already done part B here, so I might encourage you to pause the screen and read through that one just to make sure that that one makes sense to you. But The idea here is that whenever you start to take a look at enough examples of rational functions, this always happens in math, where you take a look at a number of examples, you start to notice patterns, and then you might be able to suspect that those patterns would lead to more general rules that you can use, and then you can prove those results and use them as tools to solve problems. That's pretty much how mathematics goes. So one thing that you might see here is that there is a pattern between the numbers playing the role of h and k and where we placed those vertical asymptotes. So if you look at those numbers for h and k, in example A, that was -3 and +4 respectively, we ended up with some asymptotes that are very, very similar or related to those numbers here. So your vertical asymptote again was x equals 3, your horizontal asymptote was y equals 4, and those are literally the exact same as the two numbers playing the roles of h and k, okay? Remember that for that number h, though, that is going to have to be something that we typically change the sign for, and we've seen that for other different types of functions as we've taken a look at these values of h and k. Same thing for over here in this other example, right? So playing the role of h and k in part B would be +3 and -1, and remember you got to change the sign of your h value to get your vertical asymptote, but then you literally just use the same k value, and that is your vertical asymptote, or your horizontal rather, okay? And so using these shortcuts, it gives us this way to figure out what our asymptotes are without even ever having to look at the graph in the first place. And so that's something I want to summarize down here, right? So if you notice the pattern, you have reciprocal functions of the form given there with a and h and k. We basically look at those values for h and k, and those tell us where we might place your horizontal and your vertical asymptotes respectively, okay? So to write down something for your vertical asymptotes here, those would always look like they have the same exact equation. Keep in mind those are vertical lines, so those would be a vux. They would start off with x equals, and horizontal asymptotes, those are horizontal lines, those start off with y equals, okay? The trick here is that you just want to borrow the opposite sign of h, okay? And so in general here, that would be writing that down as being able to say the opposite sign, or negative h, whatever it is, okay? So basically you just take a look at whatever number is sitting right here after x and you change its sign, and that's where you put your vertical asymptote. For your horizontal asymptote, you just go ahead and look at the value of that k number that you tack on to the fraction. No need to change the sign there. It's just going to be y equals whatever that k number is, okay? And so again, that gives you a really nice shortcut for being able to ignore the graph completely, but still be able to tell me where you would place those vertical and horizontal asymptotes. And so I want to go ahead and get some practice with that here. Example 2, it just basically says to graph this function and identify the horizontal and vertical asymptotes and then state the domain and range. I've already gotten us a head start here in this problem by going ahead and drawing it, but again, just using some of those shortcuts that we just talked about, we notice that playing the role of h here in this example, it's going to say +2. And keep in mind, whenever you move on to finding your vertical asymptote, we're going to change the sign of that number. And so the vertical asymptote would read here, x equals, the opposite sign of that number would be a -2, and that's why you see on my graph that I've gone ahead and jumped 2 grid squares to the left and then put my vertical asymptote there. I dashed that in gray. Okay, playing the role of my number k, it looks like is -4, and so keep in mind that is your horizontal asymptote. So we'll say here y is equal to -4, and so that is going to mean that on the y-axis, I'm going to go ahead and from the origin jump down 1, 2, 3, 4, and then that is where I put my horizontal asymptote. Okay, so again, there was no need to look at the graph for that. We just simply look at what's playing the role of h and k, and that gives us a little bit of a shortcut way of being able to figure out where those asymptotes are. And now that we know where these asymptotes are, we can go ahead and get their domain and range really simply, because it's always the same for any rational function. You just go ahead and use all the values except for these asymptotes. So for the domain, we're looking at the vertical asymptote. We would say the complete set of all the numbers except for -2. So we would go ahead and unite these two sets that are separate from each other at that value of -2. Same thing for the range. We're going to look at the horizontal asymptote there. So from -infinity all the way until we reach that horizontal asymptote, unite that with -4 all the way to +infinity. Okay? And so again, there's really no need to look at the graph at all. We just looked at the function formula, and immediately we're able to tell all of this different information here. Okay? So that's pretty nice. Now, as far as getting the graph itself, the very first step of drawing the graph of a reciprocal function would be to go ahead and draw those vertical and horizontal asymptotes in. We would do those with some dashed lines because it's not really a part of my final product that I want to graph. It's not a part of the path of my curve, but it is something that I definitely want to signify in the picture, so I do that with some dashed lines. And then we're going to draw the hyperbola by just going ahead and filling out a table of values. Now, an easy way to do this would be to pick some values yourself and plug them into your function and get the corresponding outputs and then plot them as input-output pairs, but we would be here all day. That takes a lot of time, right? So just remember that the TID4 calculator can do that for you, okay? So whether you have a one that you own or maybe you have the emulator on your device, this is something that I would expect you guys to be able to do. So we'll run through the process here, right? So to graph something in the calculator, we're just going to go into the top left-hand corner of the keypad where the button y equals is. We're going to press that, and then this is how we graph any function. So you have a bunch of y's here. They're all numbered. They each say y equals, and keep in mind that y is the output. And so whenever you want to graph something, you're not going to go ahead and type the f of x equals because that's the output part, okay? We want to type in what it actually does with the input. So this part in yellow here, this is what we're going to type in as y equals in the calculator, okay? And so we're going to type that in. And keep in mind how to type in a fraction in the TI-84. If you're working with a TI-83 calculator or earlier, then it does not, unfortunately, have the fraction capability. You would just have to go ahead and use the division symbol if you wanted to type in a fraction. But here on the TI-84, we could just simply press alpha, y equals, and then brings up this tiny menu. We just want the first one, n over d, so press enter to pull it up, and then it puts our cursor on the top of that fraction. I'm just going to go ahead and put a 1 up there, and then arrow down using my down arrow button, and then go ahead and press my variable button, and then we want to go ahead and say x plus 2, so I'm going to pick up with a plus 2 there. And keep in mind your cursor is still down below in that fraction, so we're going to have to use our right arrow button to arrow out of that, and then we're going to go ahead and pick up with the rest of our function formula here, which just basically says minus 4. And then press enter here. And that locks it in as y1. And so that is something that if you now go ahead and press the graph button in the top right-hand corner, it'll give you a nice sketch of what the path of that graph would look like. And you can see here that it does make a hyperbola shape. One thing that you definitely see it does not do is it does not put those dashed lines in there for your asymptotes, okay? So that is going to have to be something that we rely on our own methods for doing instead of relying on the calculator to do, all right? Now, this gives us a good general shape of what it would look like. We want to get a nice table of values, and so the next thing we would do is we would press the second button and then the graph button again. And this brings up a big table of values, and you can use your up and down arrows to scan through all the inputs in this table and get their corresponding outputs. One thing I want you to notice, if I come down here to an input of -2, is it says that the output is actually an error. And the reason for that, again, if I go to the graph, is because that's where we put our vertical asymptote on the graph, is at -2. And so that is going to be the reason why it's going to say error in the calculator. This would be an input that would make the denominator of our reciprocal function 0. And we can never have 0 in the denominator, and so that's why it says error there. But you have a bunch of other input-output pairs, and I would just encourage you to pick out some that are nice and easy to graph, like namely, say, some integers like -3, -5, or -1, -3. Even these ones that have some point values that are 0.5s, those are nice and easy to plot because that would just be half of a grid square somewhere, okay? And so I picked a bunch of values from this table from the calculator. I picked these to fill out in my, my table. Again, you could pick more or you could pick less. Basically, the idea with plotting points is you just want to get a nice general skeleton for the shape of your graph and plot those up and just kind of, along with the asymptotes, sketch the rest, right? So you notice that my end behavior up here and down here, it gets gradually closer and closer to those asymptotes without ever touching it or crossing it. And same thing with the end behavior over here and here. It gets gradually closer and closer and closer, but it'll never touch those asymptotes or cross them, okay? So that's just a little bit about reciprocal functions and how we can take a look at different characteristics of the graph. So I hope that that's all made sense to you. If you guys have any questions, let me know. But look out for part 2, where we're going to be picking up with this discussion and talking about rational functions. So I will see you in the next one.